to time, it may keep going. Some of them are higher magnitude, some of them lower magnitude. So if you take DC negative pole, the radio interference pulses are smaller in height compared to positive pole, but their frequency is higher. They're more high frequency current components propagate along the conductors and produce radio interference near transmission line. Okay, compared to AC. So you see these magnitudes. AC has also, you have these pulses, but the magnitude and the time duration or frequency, how often they happen. This is the positive cycle, for example, in the AC case, and the negative cycle. When the AC waveform becomes negative, you see negatives is similar to DC, but magnitudes are about the same here. But if you consider AC magnitudes are similar to DC magnitude, but the frequencies are different. So this is how you compare radio interference compared to an AC line. Okay, DC pole, negative pole, DC positive pole, DC negative pole. Coming back to this waveform, I told you about gap discharge. When you have a gap discharge, you have a steep up front reaching a maximum current and then going down. So what are the time frames for reaching to the maximum is 1 to 50 nanoseconds, and decaying the tail is 50 to 200 nanoseconds as shown for gap discharges, both positive and negative corona, as well as gap discharge. This is the current wave shape that you could, it's like a very high steep front. So some numbers for the amplitude of the current in milliamps, rise time, duration, and all that is given here, both positive corona, negative corona, gap discharge. So those are the numbers. And for again here in this case, frequency spectrum of these positive, negative gap discharge is given here, frequency spectrum in megahertz. So all that. In the interest of time, I have to go fast. So radio interference characteristics comparing to DC and DC positive and negative pole versus AC lines is given here again. The frequency spectrum and then lateral profile. So the distance, as you see the distance, this is where the conductor is in the middle. As you go away from the conductor, those radio interference levels in decibels are lower. That's that's how it works. Statistical calculations are given here. Statistically, because different lines behave differently, so you take a statistical number when you come up with some average numbers, all that. Lateral profile is given here. Again, distance from the conductor to the radio interference levels. Similarly, for DC lines, again, statistical distribution is given for comparison purposes. See, the other thing is audible noise. We talked about radio interference, those pulses, the current pulses impacting the radio waves. Now we are talking about the audible noise, which is going to impact the living beings like us. You cannot have too much loud noise, right? So there are restrictions, the decibel standards are there for audible noise. So again, some curves here shown here. Similarly, for audible noise from AC lines is shown here with the frequency spectrum. Corona generated hum noise. I mentioned earlier the hum noise has very different pulses here with a high frequency, and they're really twice the power frequency. The hum noise is for a 60 hertz frequency, you have 120 hertz hum noise frequency. So for the audible noise. So lateral profile, statistical distribution, these are the terms that we use in the literature. Those are all shown for DC lines also here, and also DC electric fields and space charge profiles, which we discussed earlier, from the distance from the center of the line. Ultimately, the corona effects design the criteria, line design criteria. So you can have a low cost design of the conductor, but if that gives more corona loss, you don't want to go with that. You need to consider an optimal design, so which has less corona loss also. So coming back to some numbers that you use for various things that we talked about, the radio interference I didn't talk much about the television interference numbers, but the radio interference and audible numbers, the design limits that we use in USA for different voltage levels are given here. The decibels given here, 43, 49, depending on the voltage level. You are doing a 600 kV system, for example, so 60 in USA. Canada also has design limits, and these are some numbers given here. Coming back to audible noise, also there are some numbers given here. Audible noise during daytime are higher, 55 decibels, and outdoor environments, and indoor environments is 45 decibels. Indoor environment. These are the limits that we follow in North America. So, Environmental Protection Agency, EPA, dictates these numbers. So we have to design such that the audible noise that we get either from AC lines or DC lines should be lower than these numbers. Okay. So DC fields and DC ions design criteria is given these two numbers to remember. The electric field is 25 kV per meters. That is the limit that we use for the design. The ions has what is called the ion current that is generated is 100 nanoamps per meter square. So if you take a 1 meter square of area, the current that is flowing through should be limited to 100 nanoamps. That is J, that is defined as the ion current density. So you need to limit that when you do your calculations. We have software to do this. We hear more about this from John and also our TLW, the workstation, which calculates some of these. So I don't want to go too much about those, but just to now, another aspect I want to give you is the live working. Live working means working on the transmission lines, either AC or DC lines, without taking the lines off, still conducting the current and energize it to the voltage. Different things like over voltages, space charge, electric field, magnetic field, all that. And then how the differences between AC and DC are all documented here. So again, in the interest of time, I may not go through all this entire table. So it's a good thing for you to look for. You might wonder what is MAD. MAD is an abbreviation, okay? So it's called minimum approach distance. That means you are working on a live conductor, how close you can go without being electrocuted. A person can go and start changing some things on the line, right? So minimum approach distance, because of the space limitation, we just call it MAD, MAD. So we are doing at EPRI a lot of tests, energizing the lines for AC as well as DC, and changing the configuration of the lines, and changing the distance. What we call bucket truck, where a person will be sitting on the truck and changing the insulator, for example, a failed insulator, things like that. How far he has to be so that he won't have any problems or electrocutions, things like that. So those are things, research we are doing, and some ultimate goal is to come up with some standards, how far you should be away from the live or energized conductor to do any operation and maintenance issues, or changing equipment or insulators, things like that. So what kind of issues for voltages, all this, and how they affect for AC lines versus DC lines. So that concludes this presentation. Maybe what I will do is I'll also finish the other presentation, and then we'll take questions, or do you want to do questions here? Tell me. Questions first? Okay, let's have some, because this presentation will be continued, this topic will be continued tomorrow again. We'll have more information tomorrow morning. But certainly if you have some quick questions here, please raise some quick questions. These are basics of Corona I covered. Okay?
질문한 뒤에 한 12시 한 10분쯤에 전투투자를 하고 가려거든요. 그러니까 지금 슬라이드에 대한 내용 중에서 질문을 먼저 하시고 얘기하고 그 다음에 슬라이드 넘어가는 겁니다.
Any questions? Did you understand everything? The physics? Yes.
날씨가 바뀜에 대해 가지고 지금 9페이지부터 13페이지까지 날씨가 바뀜에 대해서 이제 DC 코로나가 바뀌는 특성들이 있잖아요. 그게 이렇게 이온화가 되는 과정이 어떻게 관련이 되는지 그
날씨에 따라서요.
네네네.
Okay, based on the weather conditions,
Yes.
The corona is changing. So
Yes.
according to the DCs, what is the can you define what kind of weather create what?
Yeah, I'll summarize that, but John, his presentation will be more detailed. In general, in AC lines, when you have rainy weather, rain and things like that, you have more corona. Whereas in the case of DC lines, a nice weather is more corona than what we call rainy weather or foul weather is okay with the DC lines. You have less corona in a rainy weather for DC lines. For AC lines, rainy weather, wet weather might cause more corona. So there is a basic difference. So those two, but we'll have more information on that. John, you want to say something more?
코로나가 더 많이 발생을 하게 되고
Yeah. So
우천시는 DC에서는 코로나가 적게 발생을 하게 되는데
yeah, if you think of DC lines, weather is good, no rain, there won't be any corona. That's not correct. In DC lines, you will have a fair weather. We call it FAIR. Fair weather means clear, sunny day, nice, everything. You still have a corona issue with the DC lines.
날씨가
Yeah.
이제 뭐 화창한 날씨에도 DC 라인에는 코로나가 생길 수 있는
많이 생기는 거고 레인 데이에는 더 적게 생기는 거는 이해를 하는데
Yeah.
왜냐면 체인지 바뀔 때 좀 더 커지잖아요.
When weather change, the point where the change to the sunshine,
Yes.
shining,
Yes.
is there any effect differences between the AC and DC in terms of corona?
Yeah, sure. Yeah, suppose it's raining now. Your AC line, take AC line, you have more corona, and suddenly it becomes sunny, that will reduce. The AC corona will be reduced. Whereas if you take DC lines, if it is raining, less corona, and it becomes sunny, you will have more corona with the DC lines. It's just exactly opposite, AC and DC.
H랑 DC는 완전 이제 반대로 이제 코로나가 생성이 되는데요. 그 지금 말씀하신 게 변화 시점을 말씀하시는
Yeah.
건지
변화 시점에 좀 더 커지는
What's the reasons?
From the sunny to
There's a reason. Yeah.
I'll go over tomorrow because
Yeah.
tomorrow, first thing in the morning, we have electrical effects.
Yeah.
Yeah.
He will give more details on that.
질문하신 부분에 대해서는 저희
Yeah. John Chan is going to get into more details.
첫 번째
Yeah.
그 이제 커버할 부분 중에 하나거든요. 그래서
Yeah, in a simplistic way, you think of these positive ions and negative ions, I told you, when you have a rain, those will go away, far away, and then the electric field will be a little bit more uniform when you have rainy weather and things like that. In the AC case, whereas in the DC case, the electric field will be more distorted and you'll have more corona, even in a fair weather. So simplistic way, but you will get into more details on that. Yeah.
닥터 좀
Yeah.
내가 깊게
Yeah.
세션이 잡혀 있기 때문에
Yeah. Any other questions?
Is there any reduced corona percentage level? Is there any
Is there any
method
is there any method to reduce the
Oh yeah, different configurations. Yeah, we have also like putting positive pole, negative pole at different locations and different distances, orientation. You could also change the corona performance, yes. I think you have some slides on that
I
too.
will go over
Yeah.
some of those. Like
Some slides.
just going over
The basics. Yeah.
stuff. Then I'll
Yeah.
go over to more electrical stuff.
Yeah, suppose, say you have 3 conductors, AC conductors, you are converting that to DC, which poles you want to use those, like the outmost poles, positive, negative, or if you are vertically, you have 3 conductors, 3 lines, You're converting AC and DC. You put DC positive on the top or DC positive in the bottom. That will have a different corona performance.
In case
So-
of the AC system, there is more bundle, it's less corona.
Exactly, that is another thing also. You can design your number of conductor bundles to meet your corona performance. That is the main design criteria. John is going to talk about it tomorrow. Yeah, that's why this topic, after tomorrow's presentation, you will understand more. Then you can ask more questions on this. Those will be covered tomorrow.
오늘 드리는 교육 과정은 그 HVDC 가장 기본적인 베이직 과정에 대해서 이제 아주 그 기본적인 그 팩트만 말씀을 드리는 거고요. 내일에 오늘 드렸던 이제 교육 과정의 연장선상에 의해서 조금 더 이제 깊숙이 짚어보는 세션을 갖기로 지금 예정이 되어 있습니다.
Okay?
Hello, I'm going to ask you the
Yeah.
simple question.
Yes.
Actually, I just think about if I can see the ion
Ions, yeah.
from the conductor.
Yes.
If I can see the ion, it is very happy for me. And maybe have you ever researched to see the ion from the conductor by naked eye?
Naked eye, I'm not sure, but we have actually experienced.
Kind of some facility.
Yes.
Device,
Device
or,
use,
or
The corona cameras we have installed, they take pictures. You could see that the ionization. But with the naked eye, yeah, you can feel it. Yeah, you can feel it. See, we have energized DC lines, and I think John has some slides, so you can stand underneath that. Personally, I stood underneath that line, and then exposed to that for some time, and then I touched a ground or a rod that is grounded. I see a discharge from me to the ground, get a little shock. So you can feel it, but with the naked eye you cannot see, but you feel uncomfortable. Your hair, for example, will stick out with the space charge.
Have you ever researched about the device to use, device to see the...
To see the ions itself, I'm not
I'm
sure.
not aware of it.
No.
We have, we
No.
have
Yeah.
like Wilson plate to
Yeah.
catch it.
Catch it, yeah.
But we cannot see it.
Yeah, you can measure the ionization current, but not the ion itself. You cannot
We
see.
can see it in a way that we can see the meter.
Yeah, the meter
You
current.
measure it.
You
but
measure the
cannot see it
amperes.
with naked eye.
Yeah, you can measure the current.
kind of device.
Discharge, you can see it
Yeah.
very easily.
Discharge, the lighting that is coming out of this lighting, I talked about that. Lighting discharge, you could see that, but not ions themselves, because they are so tiny particles, with the naked eye you cannot. But the effect of them on human beings or even animals, you could feel that. And you exposed to that, you could discharge to that. Just like, you in a winter day, you touch a door, like a static charge, doorknob, for example, you will have a little bit of sticky thing, it's just a little shock, something like that. And then we did a lot of studies, we have what is called human sensation, It varies from adults to children, men to women, and we have more details on that. We did at April Lennox Labs, a lot of data is available. Human sensation it is annoying. It's not dangerous per se, but it's annoying because you get little shocks and you feel annoying. So if you are underneath those DC lines or even under AC lines, you may have these
We are
issues.
also doing
Research in that area? Okay.
Feel the kind of ion and some shock
Okay.
under the line.
Okay.
Gochang,
Okay.
Gochang province area.
Oh, okay.
Yeah.
Okay. So maybe we could share that information with what we have done at Lennox Labs and what you are doing, the human sensation levels and all that. That will be a good area to work on that. And these ions, as they keep coming out, there is what is called saturation. After some time, the whole air between the conductor and the ground saturates, and then we have some information on that. Tomorrow's slides will give you that information. Any other questions, comments? Okay, I will go to the next presentation briefly. Yeah.
Questions about page 45.
Which number?
Page 45.
45, okay.
Current effects design criteria.
Okay, yeah, these numbers, yeah.
Yes,
You said the power system is governed by FCC rules. I
Yeah.
want to know what is FCC. And one more question.
Yes.
That the table is for the AC lines.
FCC is,
What
yeah.
about in case of DC line?
Oh yeah, the DC lines, the corresponding table, I don't have it, but we generally use the same numbers for AC and DC at this time, okay? Because we didn't do a lot of research, we didn't have that many DC lines. So we are using the AC standards for DC also, but with EPRI research and others research now, we are trying to modify these numbers for DC because we are getting more data, and we are also measuring some of these parameters under the actual lines. We have a project, John is going to talk about it. FCC stands for Federal Communications Commission. This is a US organization for US. So what they have set some standards in terms of radio interference levels, you know. So that's a federal government organization. They tell all the utilities to follow these standards, these limits. So these are numbers given for AC lines, but the similar numbers we are using for DC lines. If you have a 500 kV or 600 kV DC line, you still go with that 60 decibels number right now, because we didn't get that much research done in the DC area to change these numbers. This will be ultimately changed for DC because DC is different. But we have only few lines compared to AC lines, so we are just using same numbers. Yeah. Okay. You want to translate or is it okay?
Also to Canada, they adopt.
Yeah, Canada has a similar to USA. They have the same. Yeah, yeah. Canada has a similar numbers they use. The whole North America is the same. In fact, all over the world, some people also copy these numbers they use if they don't have any standards, because even Europeans, they use this. So actually the idea in the future is to measure underneath the energized HVDC lines, measure these things and see are they still within the limits or what else we have to do to reduce them or increase them. All that is the research topic. That's what we are going to do in the future. And we started some projects measuring what is called electric fields underneath the energized lines. We have a project. So that is, John is going to cover, you know, ESCOM, South Africa lines, Manitoba Hydro lines, and BPA lines. We are putting some instrumentation under the exact lines, actual real lines, and come up with some numbers in the future.
Can you tell me one more time about what this FCC stands for?
Federal Communications Commission, FCC.
Federal Communications
Yeah.
Commission.
Yeah, I think that's correct. Google it. It's a federal body, federal. Yeah, so it's basically federal government in Washington D.C. They have set some standards for radio interference from power. Yeah. Because this is radio interference is interfering with the radio signal.
Yeah.
That's why they put some limits. Yeah.
That's why
Yeah.
the communication
Yeah.
committee.
Yeah. Okay. Any other questions, comments? Okay. Let's go through the next presentation then. I'll have about 15 minutes. This is an important topic that I want you to. Could you please put that presentation for me? The AC to DC conversion presentation. Can you? Someone help me put that. Okay, what we talked so far in my presentation is basics of HVDC, first presentation. Second presentation, basics of Corona. Okay. Now, what I want to introduce to you is a new thing, you know, what is called converting an AC line, because you already have an AC line, convert that for DC operation. If you convert that for DC operation, why do you have, first of all, why do you have to convert? Because you want to increase power on that line without building another line. Use same AC conductors, put rectifier on one end of the line, inverter on the other end of the line, change the insulators, because AC insulators won't work for DC. because DC is different. DC voltages are different, constant DC voltages. And also you operate at a higher DC voltage than the AC RMS voltage, so you need more insulators to support that from the pole to the conductor. So ultimate goal is to push more power on the existing corridor. So what we did at EPRI is maybe about 6-7 years ago, we started research in this area. The reason being, a lot of US utilities and even other parts of the world are constrained to get new rights of way to build new lines. Use the existing line, existing right of way, do some of these extra things, and then push more power. That way you can meet your load growth. For the time being, you could meet the load growth, don't need to worry about building new lines. So with that preface, so we did a lot of studies. I'm going through these slides a little fast here, but what kind of gains you can get, what are the issues to look for when you convert an AC line for DC operation. Okay, I think the industry needs, I already talked to you, because building new lines is difficult, getting new rights of way difficult. So let's see, we can push more power on the existing AC lines, right? So we have, before I get into the AC line conversion to DC operation, we have a lot of other options also you should be aware of to increase power on an existing line. I don't know whether you heard of this dynamic ratings. That means you don't do anything except you monitor the weather, temperature of the conductor, or the sag of the line or a tension of the line. One of those three, temperature, line sag, tension of the line are all related. Okay? If one of the parameters you can either with a tension monitor or a sag, video sagometer we developed with a video camera mounted on the pole. So if you monitor those are within the limits. You can say this line is, you can put another 10% more. When you have a peak load, just push more power on that line. That's called dynamic ratings, means changing the ratings from a fixed static rating. Say this line carries 100 megawatts fixed static rating, right? You had those for all worst conditions, for too hot day. In summer, you consider that as the peak. That is so you have to design your line for one rating, which can be applied for any condition. Instead of that, change the rating based on the ambient conditions. It is a nice cool day today, a lot of wind is blowing, the conductor gets cooled, you could push 10 to 15% more power. So you monitor those, weather monitor, sag monitor, all these put monitors on the conductor at few spans, and then you say, I can increase power on that line. That is called dynamic ratings. That will increase 10 to 15% power on the line. FACTS controllers is like power electronics based controllers. They can also increase the phase angle difference or change the impedance in the line or increase the voltage at the bus close to 1 per unit. They can also change power flow, maybe 30 to 50%. So if you install FACTS controllers, you could do that. Another thing that is happening in the world is the high temperature low sag conductors, means you have the ACSR conductors which have been used for many years now. They have a rating of say 100 megawatts on that line. Without changing the towers, you put a high temperature low sag conductor like ACSS or 3M conductors, and John has done a lot of work in that area. Take this old conductor, ACSR conductor, put the new conductor. The advantage of these high temperature low sag conductors is low sag, means the clearance from the middle of the span to the ground will be the same as your ACSR conductor, but the material that you use for this conductor is different, and it can carry 100% more current in that line, but it won't sag more than what your ACSR conductor is. You can put that, you can increase power flow also, but then you are replacing the conductor. Okay, take out your old conductor, put new conductor. That's one option. Some places you do that. It's required you do that. But the option that I'm talking about is use the existing AC conductor, whatever you have, put rectifier and inverter at both end of the line, increase the capacity on the line. So this is the option I'm talking about. So you have many options to increase power flow on the line, as some of them are listed here. So let us see what are the factors that dictate converting AC line for DC operation. Okay? So basically, because you have AC 3 conductors, 3Y, this is a DC line shown here, but as I mentioned already, structures you don't change, conductors you don't change, insulators you have to change, terminal substations you have to add, and also you might have to go to the government and get re-permit because you are operating DC at a higher voltage. DC is different than AC, so you need to get permit. You are doing these changes. Just like in our house, you add another bathroom or another room, you go to the city and get permit. Same thing, like here we have to go and get permit because you are changing the thing. What exactly we are doing by doing that is really we still have to limit all these phenomena we talked about, corona, insulation, NESC means again the safety, National Electricity Safety Code we have in North America, NESC, and the electric fields at the ground. All these limits we still have to consider when you convert AC line for DC operation or any of the options that I talked earlier. So how do we get this extra power? You know, lines, if you consider AC lines, thermal limit could be say 200 megawatts, but because of stability, we may be operating them only 100 megawatts or even lower. The thermal limits is where the maximum current you can get through that conductor, right? In the AC systems, because of surge impedance, the impedance of the line, all this stuff, we are going to limit how much current that's going, AC current that's going in the lines. If you convert them to DC, that's a different thing. You could always push those to close to thermal limits. Okay? So this is the advantage. What we are really taking advantage of is the voltage. You operate the DC at a higher voltage. So let us see, if you have a single circuit, you have 3 phases, outer phase, inner phase, and outer phase. You can have a positive pole here, negative pole here. This line could be used as a metallic return. Or you can have a tripole concept we generated. We can have a positive pole here, negative pole here. The third one becomes positive for 5 to 6 milliseconds. After that it becomes negative. Positive and negative. That way you could push more power. It's called tripole configuration. If you have a double circuit line, one AC circuit here, one AC circuit here, you can also convert both the circuits to DC, or you can have one circuit for DC, another circuit for AC. In fact, in Germany right now, there is a project they are now doing conversion, one circuit for DC operation, other circuit they still keep it as AC because they have AC loads all along the line with intermediate substations, so they don't want to convert both the AC circuits to DC. So various combinations. If you have a double circuit line, you can have 3 conventional bipoles. You know, these 2 could be one bipole, these 2 could be another bipole, these 2 could be another bipole. Because you have 6 conductors, right? Or 2 tripoles. This is a tripole DC, another tripole DC. Or a single bipole. That means all 3 conductors, you could put them as one conductor and one rectifier here, and then another rectifier here. So you can have a single bipole. So basically you can have a positive pole for combining all 3 and a negative pole here. So several combinations. We did a theoretical study, came up with how much power flow increase you can get. Okay, this is a critical idea. When you have a AC, your insulation level is designed for your peak AC voltage and you are operating at this voltage. But DC, you can increase the voltage. When you run same conductor, you are running for DC with the conversion, you can run at 1.55 times the peak AC voltage. Of course, we still have to go through these limiting criteria: conductor gradient, electric fields, clearance for insulators, all these we have to meet. So by having this DC voltage higher than the AC peak voltage, keeping the current, the amperes, AC RMS current same as the DC current, you can increase the power flow. Because your DC voltage times DC current dictates the DC power, right? So that is the idea here. That's where we are able to get more. So this slide shows while AC current is limited by several factors like surge impedance of the line, voltage drops, steady state stability limits, thermal limits, whereas DC current is limited only by thermal limits. Because in DC case, we don't talk about surge impedance and reactance and all that, voltage drop and all that, or even stability limits. These are not existent with DC. So for different configurations I talked about earlier, single circuit bipole, how much power you can get by just increasing DC voltage by 50% of the peak AC line to ground voltage. So you could see a double circuit 3 bipoles, you could really get 235% increase. Say if your AC is 100%, so if you convert that with 3 bipoles, double circuit line, you get another 235% increase. Okay? So different configurations, having even DC current, if you increase the DC current also by 50%, then AC RMS current, then you can get even more, close to 350%. Here, keep DC current same as AC RMS current. Here, 50% more. So these are all theoretical, of course, theoretical numbers, but when you come to these actual calculations, you have to take your system configuration